Welcome to mathandstuff.com. This is A Squared. Today, believe it or not, we're going to do a whole course in statistics. Down at the bottom of the home page is a link to all the videos. The statistics video we're going to look at is one of three. The first was written probably 3 years ago, just as a web page. And then these other two were added as I prepared this summer to create this video. In each case, you'll find support material for the video. In this case, a web page, a spreadsheet used to produce the web page and that I use on a regular basis, a PDF file of the web page. It's about 36 pages long. You don't need to copy it. You don't need to copy the spreadsheet. You don't need to copy the web page. They're all there in case you wish them. This is what we're doing, what we're going over. Most people, when they take stat, go through all these topics and spend 2 hours, 4 hours per topic. We're not going to do that. We're going to fly through this. If you need more time, freeze the video, go back and look at it, or you freeze the video and use the support material. We begin. This is a year of statistics, and these are the handouts. These are the materials you may want, you may not. I again emphasize it's heavy on vocabulary, light on computation, and there's no counting theory except for a few things we go over to clarify. We begin. Now, I can't tell what your background is, whether this is a review for you, whether you're a teacher looking for support materials, or you're a newcomer. So I'm going to aim the talk to the newcomer. You can always speed through it, or you can slow down, but I'm not going to read the whole thing to you. That would be like reading the textbook to you, and we're not going to do that. This is a plain old ordinary fish tank with fish in it. In the non-math world, when you take a sample from the fish tank, you're looking at the fish. When you take a sample in statistics, you would be considering one at a time data or something about each fish that is measurable, countable, or classifiable. So it's not quite the same thing. If you have a collection of fish, that's a sample of it. If you have a population of all the fish in the tank, that's also a sample. It's kind of like a subset. Subset is some, all, or a set containing some, all, or none of the original set, but no new elements. All right, so here's what we just talked about. Sample, population. Population would be everything in the fish tank relative to one item. Sample, a subset of the population relative to one item. Statistical sample is a collection of raw data Statistical population is a collection of all the data. A data point, we didn't use that word, I'm using it now. Data or a data point or raw data can be used interchangeably, as opposed to a statistic, which is processed information. Two very important ideas. One is discrete, the other is continuous. Let's make it bigger. Let's go like this. I clicked on the image. You can click on the image and isolate just the image. You can also click on the image, download it, save it, do whatever you want with it. Again, discrete and continuous. Look at the purple colored in part of this number line. All the numbers between 1 and 5 are included. But if you look over here on the left, for discrete, only the whole numbers are included. And all the stuff in the middle, all the non-integer parts, all the non-whole number parts are not in the set. So when you go to draw a bar graph for the number, for a number, suppose the number were 20, you would have 5 20s. You would have 3 40s, 160, 3 80s. However, if you looked at a histogram of continuous data, notice how the bars butt up against each other, continuous and discrete. Okay, if you happen to hit the wrong button and go back through and through, and my hand sometimes slips, so that's going to happen. All right, we went through population and sample and discrete and continuous. Now it's time for you to do a little work after we again review the vocabulary. Continuous. Here's a place where you might interact with the web page. You don't have to, not important. I think it's a value. I just hit data. Notice all of these numbers give me a decimal representation. The decimal representation goes on for as far as I've made the box. That's an example of continuous. Discrete, here are 2 examples. The length of the fish measured in ½ inches. The numbers I get are either integers or halves. If instead I went the number of things, as in the number of nickels in a jar, unless you have faulty coins, you can't get fractional parts of that. Both of these are discrete. A night's win would be a plus and a loss would be a minus. Those aren't numbers, but those are things that you can count. So in a night, you might have 4 wins, $4 or $8, or you could lose 17. All examples of discrete and continuous. Again, to take a sample, it's not the same in statistics as it is in normal everyday life. Each one of those pictures on the screen is a possible sample. And there's all varieties of them. Sometimes you get all of the fish. Sometimes you get some. There we got just one. Two things are important when you take example. A sample. Make sure the sample is large enough to ensure the accuracy you need later. We will talk about that, the size of the sample. And make sure you get a random sample. If you're sampling fish in a pond because you want to know something about their length, don't just take all the fish that you find right up next to the shore. That's not a random sample. That's a random sample of the fish next to the shore, but it's not a random sample of the whole lake. Don't just go down deep and get just a sample of that. You want to try and get a random sample. Perhaps you'd have to take a sample in many spots and pool the results. Or just consider it two different populations. Okay, so words we need. Random sample, sample in which each fish is equally like to be chosen. A population size, the number of things like fish or their data points like length, either continuous or discrete, in the population under consideration. Now, this next set, all right, stop. This next, I talked to the computer, yes. This next idea asks you to look at 4 different samples. I'm going to project one at a time. I'm going to go over something on one. Then I'm going to stop talking. I'm going to show you 2, and I'm going to keep quiet. Then 3, and I'm going to keep quiet. Then 4, and I'm going to keep quiet. You could freeze it and do it all on your own. And then you should answer the questions. And what you would do is you would select the piece between the stars and get an answer. All right, all I'm going to show you is example 1. I'm going to wait. I'm going to make it bigger. This is probably what you learned in middle school mathematics. You probably learned how to do some descriptive statistics. You may even have been given a sample or had to pull numbers out of a hat or whatever. I have, when I've displayed the raw data, even begun to process it here. I grouped it, the first 10 numbers, the last 10 numbers. Then I wrote a stem and leaf. This is the stem. These are the leaves in the order in which I collected the numbers. Here's a 38. There's a 38. The next 30 was a 33. Then I took these and I ordered them. Once I did that, here's the raw sample. Here's the ordered sample. Notice The 0 came from the last 10 scores. The 3 came from the first 10, and so on. So again, here's just raw data. Then I did some statistical computation, and I found the mean and the standard deviation. And you probably heard the word mean before. There is, let's go back to here. And let's go one more. Let's go to here. No, let's go to the first page. All I'm attempting to show you is there's a whole dictionary here, if you wish it. I'm going to look up the word mean. Mean, it's the arithmetic average, the sum of the numbers divided by the number of numbers added. A lot more information is here. I want to go back. I want to now look at the word average. One number, a one-number representation of a group of numbers. Usually we do the mean, mode, and median. You could research all that. Back to the home page, we don't need that. We were looking at this. We got as far as mean. Standard deviation is not a measure of center as the mean is, but a measure of spread. The other measure of spread that you learned in middle school was the range. In addition to finding the center, which is the arithmetic average, right there, it's called Q2, or the 50th percentile. That's right in the middle of the data. And I averaged the 23 and the 26. The average of those two gave me 24.5. That's right in the middle of the data when it's ranked lowest to highest. The first quartile is the mean of the bottom half. The third quartile is the mean of the top half. You probably, if you had if you had middle school in the last 20 years, you learned all that and a little more. You learned box plots, and this one's a box and whisker, and here's bar graphs. Let's go back from that. And we don't need this one. I'm going to keep quiet. You're going to look at sample 2. If you need more time, freeze the video. Sample 3. If you need more time, freeze the video. Sample 4. If you need more time, freeze the video, but I'm going to give you a little more time on this one because this is where I'm continuing. The point I'm making here is this is pretty choppy. We took 12 coins, tossed them, counted the number of heads on those 12 coins, and we did that experiment 15 times. Then we took the 12 coins, tossed them, counted the number of heads. So in this case, our data point is a number, and we did that experiment 30 times. Here we did it 60. Here we did it 120. It's kind of taking a shape you might remember. Okay, here's where you get to think about the questions. I'm going to give you a little time. If you need more time, freeze the video. I'm going to begin going over it very quickly. I want to know which samples are continuous and which are discrete. Swipe between the stars. That means hold down the mouse and pull. In example 1, how is Q1 the 25th percentile? In the ordered data, so in order to find a percentile, you have to order it. See that in the leftmost purple area, the 25th percentile is 9, exactly between 8 and 10, the arithmetic average. Notice that this technique is also used for finding Q2 and Q3. Which sample is more symmetric? You might not remember that word. Symmetry, a correspondence of parts. The human body has, and the human face has bilateral symmetry. A point could have radial symmetry, like this one. And I think I can close that one and go back to here. So, which sample has more, which sample is more symmetric? Sample 1 or sample 2? If you don't know, freeze the video, go back, look at the samples. Here's my answers. Sample 1 is in the stem and leaf plot. The median is more in the center of the box with sides Q1 and Q3. The right and left whiskers on each side are both about the same length, so it's more balanced. Is there anything in sample 4 that might be omitted? Because there are only 12 coins, no data points would have 13 or more heads. Those numbers might be omitted from the horizontal axis. You probably have some experience with flipping coins. If you flipped 12 coins, how many would you expect to be heads? Flip 12 coins. How many do you expect to be heads? You flip 12 coins, you expect 6 to be heads. Would you be surprised if there were 7 or 8 or 4 or 2? No. 6 is what you probably expect. Doesn't have to be. If you got a whole lot of different numbers than that, then you might expect that the coin was weighted in some way. All right, the words we went over: sample size, ordered data. That means it's sorted, usually from lowest to highest. Frequency is the number of occurrences. Often we say F of whatever. Frequency distribution. This was done with a spreadsheet. Bar graph, histogram, stem and leaf, capital sigma. We did not go over that symbol. It's a math symbol, meaning add up the terms. Sample statistics, number obtained by looking at the data in different ways. It could be used to create a purely numeric picture. It could be used to create a graphic representation. It could be used to stand in as a numeric description, or it can be used in testing if things about the population sample, wondering if they're true. So we go back to center. I said words for center were mean, mode, median, and average. In the symbolic representation of how to get a mean, you add up the scores and divide by n. Now I think we'll go to a resource I've given to you that you're welcome to download, and that's the spreadsheet. If you click on it, you can download it. I have mine already downloaded. You never remember where you put them, but please try and remember the name you give it. Here's the spreadsheet I'm looking for. It's the stat spreadsheet. And I'm going to open it. And you'll notice that I have named it with a date. So when you download it, it's just named stat.xls. These are the things on the spreadsheet. The reason I'm taking you here is to look at mean. There's the symbol for how to compute the mean. And look, it's got a line on top of it for the X. This is read as X bar. It says you add up the data points, divide by the number of data points you have. I have laid out the page so that you can add 10 numbers, 20 numbers, 30 numbers. I just did it because that's how many I usually use when I write a test. So you're getting a copy of the spreadsheet I use when writing a test. That's a 99. Let's change some of these scores. Let's make that an 80. Let's make that a 60, 75. So they look more like test scores. 74 is good. 70 is good. 69 is good. Let's make this 55. And let's make that 2. The average of the scores is 63.8. The sum of the scores, 632. The next thing we'll go on to is deviation, but not yet. All right, you knew where to find the spreadsheet. Let's go back to the web page. The center, mean, mode, median. The symbol for mean is X bar. The symbol for median is X hat. You don't have to know that, but I'm going over all of the material. Spread. When you were in middle school, or even earlier possibly, you learned range. The spread of the data from highest data point to lowest data point. X max minus X min. In middle school, you learned interquartile range, which you saw on the box plot in Whisker. You want more information? There it is. Variance, I'll get to in a second. Standard deviation is another measure of spread. A new symbol. Sigma, that's a lowercase sigma. That's an uppercase sigma. So what this says, using order of operation, and if you don't know what that is, go back to the dictionary, look up order of operation. The innermost thing you do is you look at a score, a data point. You subtract the mean from that. You square that difference. That difference is called the deviation. So you square that, you divide by n, the number of data points you have, and then you take the square root. Why? Because I'll show you in the spreadsheet. Find the spreadsheet. There's the symbol. There's the computation. Lowercase sigma, Greek letter. Want to look at spread. Standard deviation is the average spread relative to the mean. The average spread of the data relative to the mean, computed in the usual way. That's my definition. I don't know anyone else that uses it. I want to look at spread. I'm looking at the first box. I have 10 scores here. Every single one of them is a 5. They're all the same. There's no spread. The standard deviation is 0. In the next example, they're more spread out, and I'm just going to change them. Let's make them even more spread out. All right, so I put in a -1. That meant the spread got bigger. Let's make it even more. I'm just picking random numbers to do this with. We should get an even bigger spread. I think you'll agree I'm going to make this one have a smaller spread. I don't want to go up as high as 10. Let's make that a 4. Let's make that a 4. Let's make that a 4. Notice the spread is getting smaller. Yeah, the mean changes. You know how that works. But the standard deviation, the spread changes. Here we go with, how does that happen? You take each score, you subtract the mean from it, you square that deviation, you add them all up, you divide by, in this case, n-1. You could use n or n-1 depending on whether you want population or sample. We're not worried about that. But the idea is you're finding the average spread computed in the normal way, the standard way. I'm just going to change one score. Soon as I do that, not only will the mean change, but everything will change because I changed the mean. Let's make this, just for kicks, a 4. There we go. If I put it back to a 10, the spread should increase. There we go. Enough of that. Next thing we'll play with is a z-score. We don't need that yet. Symbols in statistics. Mean and standard deviation. They are different for a sample and for a population. Why am I being so picky? Because this will be important, quote, later in the course, further down the page. All right, you know, a data point is X. The average is X bar. The standard deviation is S for spread. In a population, we're using the Greek letters mu for mean and sigma for standard deviation. Box and whisker, we've gone over. Symmetric, we've gone over. Distributions, new word. Uniform means everything is the same. Bell-shaped, binomial. You see the bell shape. We've looked at something like that when we looked at histograms with flipping the coins. You probably have heard of a bell-shaped curve. That's an example of one. There are other distributions. We're going to just skip those and continue. Freeze your video. Take a break. Look at everything. Then we continue. New idea. Theoretical versus experimental, and descriptive versus analytical statistics. 4 different ways or uses of statistics. We've looked at experimental and descriptive, how you collect data and analyze it and depict it. We're next going to tackle analytic and theoretical. Analytic means where we start to make a judgment. And theoretical statistics is the statistics where mathematics and common sense are used to examine a situation. 4 new vocabulary words. I think I want to go to the vocabulary words first, and then we'll go back up and look at the examples. Experimental and descriptive, we've done that already. Theoretical means you gotta look at what the math is saying and what common sense is telling you. We're about to go over tree diagram. We're about to go over event. We're about to go over sample space. Analytic statistics is where we're headed. So now we go back to, and I think, no, okay, I didn't want that. Let's go back. What I wanted to click on the, okay, click on the image to go to the problems. That's not what I wanted. So I'm just going to make this bigger. You have 2 different experiments drawn here in graphic form. The one on the left is taking a coin and flipping it 3 times, listing the heads or tails result. Let's read it from left to right. Just as you read in English from left to right, tree diagrams you read from left to right. At least most of the time. I can't think of any time where you don't. Okay, so you start out at the beginning of the experiment. The first part of the experiment is to flip a coin. Assuming it's a fair coin, you're going to get either a heads or a tails. Now, there are some coins where you'll only get a head and only get a tail, but we're not talking about cheating. We're talking about fair coins. You can consider this the flip of one coin, and then the next part, a flip of another coin, and then the next part, the flip of another coin. Or you could think of it as taking a coin, flipping it, using the coin again, flipping it. Again, you have only heads or tails as the results. Taking the same coin and again flipping it. If you read the top branch, it would be heads, 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 listed here as an event in the sample space. If instead, let's take this one, tails, heads, tails, tails, head, tails. So that's the tree diagram. These are the 1, 2, 3, 4, 5, 6, 7, 8 events in the sample space. The one on the right is a very different experiment. It says, select a color from red, white, and blue. So these are all the outcomes from selecting the color. Then it says select a number from 2 and 3. Those are your only choices. And then select the other number. So if you get red for the color and pick the number 2, then the other outcome will be a 3. If you take red, pick the 3, the other outcome will be 2. In this case, you have 1, 2, 3, 4, 5, 6 events in the sample space. Why bother with a tree diagram? You can do it in your head for these. Later, you may need to justify your work, as you would have to do on a stat test. Another reason is you want to make sure you have all the events possible, especially for the longer ones. The other, it gives you credit on a quiz or a test. Again, back to the vocabulary. Experimental, descriptive, theoretical, tree diagram, event, sample space, analytical. New idea. Probability. Much of this we are not going over because I promised light on the computation. You cannot really talk about probability without doing more computation. So we're going to go through just what you absolutely have to know and focus not on how you do it. Okay, before we begin, we go over the old vocabulary. Experiment, event, outcome, and sample space. All that's old. New stuff. Probability. Probability of an event. In symbols, you could write it capital P and then in parentheses, whatever event you're talking about, or lowercase. You read it as probability of the event. So the parentheses are read as of. P of A would be the probability that event A happens. P of heads, the probability of obtaining heads. P x equals 3, the probability, the variable is 3, or the probability of the number 3 occurring, or the probability of obtaining 3 when you run your experiment. Always the probability of an event is how many times the event happens over how many events in the sample space. F stands for frequency, N stands for the number in the sample space. You have probably been looking at that since middle school also. Don't know for sure, I just think you have. Here's problems, here's the answers to some problems. Here are blank problems. We're going to go over only the ones with answers already listed. I don't think you're going to have any problem with this. You want more problems? Freeze the web page, freeze the video, go play. Find these probabilities when a coin is tossed 3 times. So the way this was explained in this case was a coin was tossed 3 times. You could also say you tossed 3 different coins, but that's not the way it was verbally described here. The probability when a coin is tossed 3 times. Here's the first toss and its possible outcomes. The second toss, the third toss. Here are the possibilities when you toss a coin 3 times. Heads, heads, heads. There are 8 possibilities. The probability of just this event, it happens 1 time out of the 8. So the probability that x equals 0. Now that's not 0, that's 3. Here's the probability that x equals 0. It only happens 1 time. Let's count the probabilities for x equals 1. So we want 1 head. Not this, not this. There we have 1 head happening once. Not this. There we have 1 head happening twice. Not this. So 1 head. Well, it says 3. Let's count again. 1 head. 1, 2. There it is. 3. Didn't count it. Let's just assume I got it right when I did it before. All right, you have to know these facts. The lowest probability, the lowest possible probability that event might happen is 0. You don't get any negatives. The reason you don't get any negatives is it's the number of. When you count number of, you don't count any lower than 0. The lowest possible probability an event might happen is 0. If the probability of the event is 0, the event cannot happen. The highest probability of an event that an event might happen is 1. If the probability of an event is 1, the event does happen. No partials. It either happens or not. That means that the probabilities go from a low of 0 to a high of 1. And all the numbers in between, depending on your experiment. Whether it's continuous or discrete, we're not getting into that. But they go between 0 and 1, including 0 and 1. It is also true that the sum of all the probabilities is 1. For example, if you flip a fair coin, the probability of heads is a half, the probability of tails is a half plus a half is 1. If the experiment is pick a day of the week, well, there are 7 days in a week. You pick a day, you get 1. If the experiment is pick a day of the week and you want to find the probability of January, can't happen. You're picking a day, not a month. Expected value is the mean. So a new meaning for mean. You knew it as an average. You knew it as the sum of all the scores divided by the number of scores you have. New definition. This is adult statistics. You're not just in middle school anymore. It's the expected value. Now, this definition has to make sense relative to your background in math and your background in speaking English in this case. One way of describing the result of an experiment is to state the value that you get, that you expect to get. In an experiment, the mean, the arithmetic average, is the expected value. We looked at that on the spreadsheet. We looked at that in the dictionary. On the left, the sample space now has 4 H's, or 4 T's, 4 heads, 4 tails. This sample space looks as it is flip a coin 4 times. In this case, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 events in the sample space. That makes the number of events in the sample space 16 in each case. Let's just do count the number of heads. We're going to count and find 0 heads. That happens down here. It happens 1 time. I listed here those probabilities as fractions, and here they are as decimals. Statistics, you have to be bilingual. You have to understand both ways. I'd like to spend a little time looking at this bar graph. Notice it's not a histogram. You can't get a 3.5. So you get a 0, 1, 2, 3, or 4. It's the number of, and you don't have partial flips, no partial heads, partial tails. So looking at the sample space, here's the sample space. There's the number of events, the number of heads. Here's the probability. If you looked at the boxes, there would be 16 boxes. 1, 2, 3, 4, 5, 6. 6 plus 4 is 10. Plus another 4 is 14, 15, 16. everything is accounted for. Has to be. And if you look at these numbers and add them up, you will get 1. So the frequency of getting a 0 is 1. The probability is 1 over 16. The frequency of getting a 1 is 4. The probability of getting a 1 is 4 out of the 16, and so on. F of X is the frequency of heads on 4 coins. N is the number of events in the sample space. The probability of an event happening is the frequency over the number of. 2 is the expected number of heads. And all of this is just doing the arithmetic. Again, vocabulary: probability, a branch of math that studies populations, samples, experiments, hypothesis, and it includes experimental, analytical, and theoretical statistics. The probability of an event has to be between 0 and 1. If the probability of the event is 0, the event does not happen. If the probability of the event is 1, it happens. Expected value is the mean, the sum of all frequencies divided by the number of outcomes. Okay, now this is not included on this page. The reason it's not included, except very briefly here, is because it would take too much time to go over all of it in words and symbols, and your eyes would vomit. I'm not doing that. So far, so good. I think you're fine. Okay, important definitions. Independent, dependent, with replacement, without replacement, order counts, order doesn't count, and factorial. Then counting methods, permutations, and combinations. We're going over the first 2 right now. We're not getting fancy. Independent events. Uninfluenced, standalone, the result of one stage or trial has no effect on another stage. For example, raw sample data is the number of heads when 3 coins are flipped. The result of flipping the first coin has absolutely no influence on flipping the second coin. Dependent means having an influence on other stages or trials. The result of one stage of collection of data has an effect on others. Let's just look at this picture. I'll bet it doesn't click. There we go. Okay, here we have an experiment where you draw 2 cards from a deck with replacement. So on the first trial, here's the possible cards. Pull out a 7. Okay, so you got a 7. Put the 7 back in, do it again. You could get the 7 twice. These trials are independent. You replace the 7. Let's look at this one. Draw without replacement. You have the first trial, you get a 7, You can't put the 7 back because that's what the experiment said. So when you do the second trial, the 7 is not in there. So you can't get 7, 7. You could get 7, 10. These trials are not independent. Back to here. Independent, dependent, with replacement, without replacement. Enough of that idea. Now we talk about order. Order could count as in you have the first, the second, the third, as in a club, a president, a vice president, a secretary, and a treasurer, whatever, in a club. They each have their own position. Or order doesn't count. The order of the raw data does not matter. For example, when you make a committee without a chair, doesn't matter how many members are listed, but they're not ranked. This is ranked. New symbol. The symbol looks like an N exclamation point. I wonder why they use that. The product of a natural number and all the natural numbers less than it. It's read as factorial. N factorial is equal to N times the natural number less than it times the natural number less than it, and so on until you get 1. 1 extra definition. 0 factorial is 1 by definition. So 1 factorial, and you could freeze it and figure these out for yourself if you want. I'm continuing. 1 factorial is 1. 2 factorial is 2 times 1, which is 1 less than 2, which is 2. 3 factorial, 3 times 2 times 1 is 6. 4 factorial, 5 factorial, 6 factorial. Look how big. Now you know why that symbol was chosen. We're skipping counting methods. You want to learn about that? Go to this link. Permutations, go to that link. Combinations, go to that link. Permutation, that's where order counts. Combinations, that's where order doesn't count. Next idea. You've seen this picture before, I think. Uniform distribution, everything is equal. This is as discrete, that's a continuous. Bell-shaped binomial, that's discrete, but they're touching. So it's faked a little. Bell-shaped normal, you've heard of a bell curve. That's it. I'm skipping the other ones for now. Let's see if this clicks. Good. Let's make it bigger. Okay. Some binomial distributions. Flip n coins, count the number of heads. You flip 1 coin, only 2 possible outcomes, 0 and 1. The frequency of when x is 0 is 1. The frequency when x is 1 is 1. The probability is 1/2 plus 1/2 is 1. For 2, you have 1, 2, 3, 4 events in the sample space. Still, the probability is 1 when you add them all up. Flipping 3, you have 1, 2, 3, 4, 5, 6, 7, 8. We've looked at that one also. We looked at this one. Again, f of x is 3, 1, 2, 3. X this time is 1. Here's 4, here's 5. I think I can close that. Go back to here. A binomial, bi meaning 2, nomial meaning number. Binomial is a discrete distribution. The raw data is the number of either successes on n independent, identical trials. That's really important. Binomial, n identical trials. You do the same thing n times. You flip a coin n times. Independent. The flip of the coin the first time does not affect the flip of the coin the second or third or fourth. The trials are independent. If it's binomial, there are only 2 outcomes, either success or failure. Usually we call those probabilities P and Q. P is the symbol for the probability of success. Q is the symbol for the probability of failure. I have absolutely no idea why they use the letters P and Q. P for probability. Q, I guess, because they figured, well, if it's not P, let's make it Q. I don't know. What is important is right here. If P plus Q equals 1, the probability of success plus the probability of failure equals 1, there's only 2 outcomes. So if you know the probability of success, you subtract it from 1 and you get the probability of failure. Here's a picture. Probability of P equals 1. There are 10 dots. All the dots are blue. 10 out of 10 is 1. No red dots. Probability of Q or failure is 0. And so on. Here, let's look at this one. Probability of success is 1/10. 1 out of the 10 dots is blue. The other 9 dots are red, 9/10. Probability statements look like probability of x equals 3, meaning the probability of getting exactly 3 heads on a trial. The mean and standard deviation of a binomial distribution are stated below. Again, a whole bunch of information on where it comes from. I'm going to skip the standard deviation. I'm going to look at the mean here. The population mean. To get the mean, all you do is take the number of trials and multiply it by the probability of success. As in, you're going to flip 12 coins. They're fair coins. The probability of success is 1/2. 12 times 1/2 is 6. I'm not even going to bother reading. Now read it. 20 phones have been poorly built. There's a 70% probability that a phone will work when it's switched on. What's the probability that at most half of the machines will run? Note that the probability of success is 0.7. You have 20 trials. That means n equals 20. You want to know the probability that x is less than or equal to 10. The words we went over were binomial, success, failure, and distribution. Thank goodness for the probability density function. Don't vomit. Just look, don't vomit. This says the probability of event X happening, as in 4 successes, 6 successes, is equal to this expression written in factorial notation times the probability of success happening X times, because that's X, and all the rest of the time being a failure. If you want to go into that in detail, here it is. When preparing for this talk, I wanted to give you a little taste of where the formula comes from. I will, before I move from here and go on to where it comes from, I just want to point out that that's X successes and Q failures. This piece is how many times that happens. Here's where it comes from. I'm going to make this bigger. I'm not sure how much bigger it'll go. Notice the date on this. Today is the 28th. So I just wrote this, but it summarizes what we've done so far. We looked at binomial distributions. What I want you to look at and focus on right now is the frequencies. I've taken n equals 5. That's this over here. And x equals 2. That's what I picked to use. Right there's the 2. So there are 32 events in the sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of the events were getting 2 heads. And this was all computed experimentally and theoretically. In this case, theoretically, because we did not actually flip any coins, but we looked at it from the theoretical perspective. But I think you'll believe that's 10. What I don't think you might believe is the formula, where I said P is the probability of success, and it happens X times. Q is the probability of failure, and it happens all the rest of the times. And this fraction is the frequency. I want to look at that formula. It's n factorial over x minus n minus x is the quantity factorial, x factorial. All I'm going to do is put in the numbers right here. So n is equal to 5. There it is. N minus x is 5 minus 2. There's the 2. Here's 2 factorial. So this is 5 times 4 times 3 times 2 times 1. You should not be lost. 5 minus 2 is 3. 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1. What this does is it cancels out the duplicates. So instead of having order count, order does not count. This says you need, out of the 5, you need to pick 2. Okay, I think you're happy with how the formula is computed. You don't know where it came from because we did not go over that in detail, but you see the 10 here gotten by this computation, and you see that the actual frequency was 10. These numbers, 1, 5, 10, 10, 5, 1, may sound familiar to you. If you had Algebra 2, then you know what a binomial squared is, or a binomial cubed. This is a binomial expanded. Here are the coefficients, and in blue, it's called Pascal's triangle. So it gives you a little idea of how that frequency was determined. I think I can close this. We're back to here. In 1733, de Moivre was studying expanding binomials as in x plus y. You could go see it in detail or explained more slowly. He was using this discrete binomial distribution. You should know every one of those words. Discrete, not continuous. Binomial, 2 possible outcomes, independent events, identical trials. Distribution, how the data is spread. Aren't you impressed with yourself? Discrete binomial distribution. That may have made you vomit before you watched the video. Now you should be okay with it. Using the formula above multiple times, he realized that with calc and the right continuous formula for a probability distribution function, again, probability distribution, how it spreads out, function, a rule, can look that up in the dictionary. He could use the calculus instead of repeatedly using the binomial formula. I lay it out here. I'm going to open up another spreadsheet that you don't need, and I'm going to save it. Open. I'm going to save it where I can find it. I'm going to save it with today's date. I cannot believe it's the 28th of August already. Okay. Why did I do that again? So I didn't lose it. Let's just go back to where we were. Here's where the sketchpad is. That's not one of the things I listed. So if you want it, that's where you have to go. Find the sketchpad. I think we want page 9. There we go. If you've had calc, you know about the area under the curve. You're looking for a probability that a score is between a lower number and a higher number. In this case, it looks as if it's solid, but I only have 32 pieces. The reason I wanted to show you this picture was to show you how solid it looked. Let's make this -2. Now you can see how they spread out. This is only 32 values for X. It's not continuous. It looked continuous, but it's not. But you get the idea that if you take enough values for X, what is really binomial looks continuous. I don't need this at all. I don't want it saved. I don't need that. I'm back to here. Okay, I hope this clicks. There we go. The birth of the normal distribution. A normal distribution is continuous. Start out with the discrete, meaning not all numbers, but select numbers. Binomial, meaning 2 possible outcomes, independent trials, identical trials, n of them, and that makes what looks like here. And I put the histograms together so they bunched up because I made the numbers small enough and I cheated. Let me just try and make this bigger. Here's a number A. That's what I'm looking for. The probability of A. Well, if you wanted just the probability of A, you want the area under that curve just at A. But you can't get that because a line has no thickness. So its probability would be 0. But if you cheat and go down a half and up a half, then you have a thickness of 1 and can find the probability. So that's why I'm saying we're going to cheat. I'm doing it with calculus. You just looked at it. De Moivre's function, mu and sigma. You know those as the population, mean and standard deviation. There is the formula. No, I absolutely do not know how he got it, but boy, I like using it. It makes a continuous probability density function called the normal distribution. And that's what we looked at. I'm getting out of here. I'm going back to here. I just want to look at the spreadsheet. Probabilities, probabilities. Here we have a bunch of probabilities. This spreadsheet will compute all those probabilities for you. Let's also look at the binomial. Here's the formula you looked at. Here are 2 samples, and I put them here to show you the symmetry of the binomial and what else shall I say? For n is equal to 4 and n is equal to 5, you've looked at those distributions. You looked at them when the probability of success was 0.5. And there's the numbers we got. This is, I think, in 16ths. That's in 30 seconds. If you have another probability that you want, I don't want to make these too big. Let's make this 10. 10 trials. Let's go with a probability that's, half of 10. If we're using fair, let's make this 0.5. The probability of getting a 3 is 0.17. Let's go with the probability getting a 5 out of 10. Just the 5 is 0.2246. So that's how you play with that page. Back to here. Gauss later worked with the normal distribution. It's named for him. It's also called the bell curve. All right, I want to go through the vocabulary. Distribution is the way the data is centered and spreads out. Again, those words, center and spread, mean and standard deviation, are really important. Function, a really dependable rule. We did not define that before. It's usually written as f of x, as in area is length times width. Frequency, you know that one. Frequency distribution, it's a graph or a table showing the frequencies of each endpoint or each data point or interval. Random variable, a number which is equally likely to be chosen, as in a random sample also, equally likely. Intervals. I think we can skip this, but I'm being very precise here. This says the score is between A and B. This says it's between A and B, including A and B. Between A and B, include A, don't include B, blah, blah, blah. Continuous, not discrete. Continuous, all numbers included. Area under the curve, another reference for you if you need it. Probability distribution, it's an antiderivative, an integral, where you want the probability of a score being between A and B. I'm reminding you, you can't just find the probability of A, because that would be just a line, has no thickness, has no width. The thickness would be 0. 0 times whatever you get is still 0. So you can't find the probability of A or of B or of 2 or of 3. All you can find is between. Normal and standard normal. Again, you've seen that formula. Mean standard deviation describes the distribution. X is the variable. The variables are x, mu, and sigma, where x is the random variable, mu is the mean, sigma is the standard deviation of, in each case, the population. X is a sample. These are for population. Everything else in the formula here is a constant. E, there's a whole web page. Oh, there's more than one page on E. There's a web page on pi. You can look those up in the dictionary. I'm not going there. This is what I want you to begin to look at. Here's the mean, the center. A normal distribution is symmetric about the mean. The mean's in the center, Also, the mean, mode, and median are all the same number. S is the spread. So here you have 1 unit of spread. Here you have 2. Here you have 3. I think we can do that in the spreadsheet. Go back to not stay9 z-score. Let's try and make this bigger. Okay, here are the numbers in your sample. That's the center, the mean. This says go out 1 standard deviation. This says go out 2, see the S's? This says go out 3. That's on a statistical sample. This is on the normal, standard normal curve. The mean will always be 0. The standard deviation will always be 1. If you wish to look at information about your sample based on the fact that you know your population is normal, and a lot of things are. We'll go into that later. But you've got to take your X scores and turn them into Z scores. Now, I hope you remember standard deviation from before. And when we did standard deviation, we took the score, the data point, subtracted the mean, squared it, added up, divided, and took the square root. Well, that piece right there, where we find the deviation, is really important. So for a z-score, and a z-score is a standard normal score. If you take your population data point and subtract the mean of, let's say it again. If you take your experimental data point, you pulled the fish out, that was your experiment, measured their length, their width, whatever. If you take those data points and subtract the mean of those data points, and then divide by the standard deviation, that will give you the z-score. In other words, this is what you started with as your sample. This is what you're turning it into. You could play with the spreadsheet. I think I have one example for you on the web page. Let's go back to this first. I'm reminding you that's a normal curve, any normal curve, always mean, mode, median are all in the same place. It is always symmetric, and usually the scores have a range of 6 standard deviations. They go from 3 below to 3 above, but they also follow some other really important features. If you're between 1 below and 1 standard deviation above the mean, because your curve is normal, we go from 1 below to 1 above, 68% of the scores, because it's normal, will always be in that range. The probability of being 1 standard deviation below the mean, 1 standard deviation below the mean, to 1 standard deviation above the mean, because it's normal, the probability is 0.68. If you go out 2 standard deviations, it's 0.95. You go out 3 standard deviations, it's 0.997. Always the case. I'm skipping Chevyshev's rule. You can read it. I'm just going over more. Back to symmetric. If within 1 standard deviation is 68%, that means there's 34% on each side. You might swipe between the stars to see the answers. I'm not, why not? What percent of the scores are below the mean? 50%. Remember, half above, half below, it's symmetric. What's the probability a score is below the mean? 0.5. Well, that's the same as 50%. What's the probability a score is above the mean? 0.5. Remember, it's symmetric. What's the probability the score is equal to the mean? 0, because you can't just get that number. There you go. What's the probability a score is greater? No, the probability a score is, let me read it again. The probability the score is greater than A is 0.6. So what's the probability a score is less than A? Has to be 0.4, because the sum of the two of them has to add up to 1. What percent of the scores are less than 1 standard deviation above the mean? What percent of the scores are less than 1 standard deviation above the mean? Well, there's 50% here and another 34% there. That gives you 84%. Okay, here's a better picture of the standard normal. The standard normal, the letter for that variable is Z. For your sample, the mean is X bar, the standard deviation is S. For the standard normal, the mean is always 0. The standard deviation is always 1. Your goal will be to take your sample statistics and re-express them in terms of the standard normal, the z-scores. The reason you wish to do that is then you know all that information easily. Here's a little table on which you could compute a z-score. And if you do the algebra, take this equation, multiply both sides by S. That's what you get. And it's isolated for X. I think you can do that. Let's just try an example. Okay, let's pick a mean first. I'm going to put in 4. Let's pick a score that's higher than the mean. Let's go lower. Okay, and let's make the standard deviation 0.5. That's what the z-score is, 6. Wow. That means it's way out here, way out there. Very unlikely, but possible. Let's make this, the mean is 4. Let's make that a 5. 2. That means right there. I think you get the idea. I'm going to skip this, you play with it. Swipe between the stars for answers. I find the z-score. You can use this. Find the probability z is less than 3. You use the tables and you use this. That's another one of the things we have in the spreadsheet. Probabilities, standard normal curve. Yeah, I don't think anybody else even has a copy of this anymore, because we have the calculators and spreadsheets and the web page to do them. It's just a table that tells you for each z-score what the probability is that your score is below, that your probability is below that. So if the z-score were 0, there you go. We're way down here, make it bigger. Slide it down. What did I want? I wanted 0. Z-score is 0. The probability that your score, that is below your score, you'd get a half. We looked at binomial. I don't think we're going to need this one anymore. Let's go to here. As I said, I don't think anybody but me even has a copy of that, except if they're like me and have it from when they were in college and or when they taught it. What we do have is we do have calculators which do the computation for us. I have resources in case you want to know that. Okay, I think you're cool with this. Given a binomial distribution, the probability that x equals a certain number is 0 because a line has no thickness. You have to use, because the normal is continuous, you have to build an interval. Here's more information about z. Yeah, about e, you don't need to know any of that. Z is the symbol for the standard normal, mean of 0, standard deviation of 1. Pi, you know that. Normal distributions, they could be peak high, peak low, be spread out, doesn't matter. You always have scores with those probabilities. Standard normal has a mean of 0 and a standard deviation of 1. Here's the table. I don't think we can click on this. Yeah, we can. If you want to know the percent of shaded area compared to the entire area under the curve, if you want to use a z-score of 0, you get 0. A z-score of 1. The probability, the score was between 0 and 1. There's your 34%. Here's 2, gives you 47%, and it's symmetric. So if you wanted 95%, you'd want half of it to be below and half of it to be above. Let's get out of that one. Cumulative normal, again, I gave you tables for that. Bell-shaped, could have any number of shapes to the bell, but the probabilities are always the same. We've looked at this. Chevyshev's rule, we skipped. Confidence interval. New idea, you've been using it all along, but I never called it that. First picture has an interval from 25 to 45 drawn on a number line. The 25 and 45, the endpoints are not included. This could be an interval in which you believe that 95% of the scores are within that interval, or 90%, or 99%. Depends on your sample and what your gut feeling tells you about it. And your gut feeling may tell you so strongly that you want to know statistically, is your gut telling you something you can mathematically say with reasonable certainty is true? So we begin with confidence interval. I don't think this one clicks. There we go. You know this already. Sample is the variable x. Mean is x bar. S is the standard deviation. Some confidence interval, number lines. The standard normal has a mean of 0, a standard deviation of 1. For a population, we're not going to use the sample symbols. We're going to use the population symbols. The mean is mu. The standard deviation is sigma. Proportions, that's really probabilities. So you're going to look at a P and population correlation coefficient, rho, not quite looking the same way, but similar. We are not doing any of this. We're doing this and this and that. Let's get out of here. So we're skipping the probabilities. I think you're happy with this. I think you get this idea of 95% are within 2 standard deviations of the mean. Why is that such a big deal? From 25 to 45 is the confidence interval for the picture we have here. And we know because the 25 and the 45 are the end points of the interval. And as it's drawn here, you can see the mean is 35, the standard deviation is 5, you're within 2 standard deviations of the mean. Means 95% of the scores are there. The probability of score is in this interval is 0.95. If the confidence interval accounts for 95% of the scores, what percent of the scores under this density function are not in the interval, but out in the tails? The tails are these regions. We didn't bother saying that when we went through probability distributions, but you can go back and look at the pictures if you wish. All right, 95% accounted for. How much is not accounted for? How much are in the tails? 5%. Okay, old symbols. Population mean, population standard deviation, z-score has a mean of 0 and a standard deviation of 1. New symbols, error, alpha. We looked at an interval within 2 standard deviations of the mean, and we knew 95% of the scores were in there because it was a normal distribution. We have 95% confidence that the score is in there. We could be wrong. How wrong could we be? Well, here's 5% unaccounted for. And that 5% is split into tails. Alpha, meaning the area out there past the endpoint of the confidence interval, has an area of 2.5 on this side and 2.5 on that side because it's symmetric. The population mean is here, and there is some distance. We don't know what it is, but if you take the mean and go up a certain number of standard deviations from that mean, that's the error. The z-score times sigma, a certain number of standard deviations, or you could go from the mean down a certain number of standard deviations. E is the maximum allowable error. These are what confidence intervals look like. I'm sure this clicks, making it bigger. Common confidence intervals. Now, when I grade stat papers, if my student doesn't give me a picture like one of these, I either don't give any credit at all, or I only give partial credit. These pictures, and you'd only use one for each kind of problem, these pictures demonstrate to me that the student has comprehension about what's going on. Here, 95% of the scores. Notice how this line doesn't go all the way up to 2. And here, well, it looks like it should have been a little lower. The critical score, remember what I meant by that? That z-score. for a certain sigma. That critical value is here, it's below the mean, here it's above the mean. We only want 5% to be in the lower tail. We want 95% to be in the confidence interval. Here we have what's called the two-tailed test. We have a mean, and we believe our mean is this value, but it could be wrong, either too big or too small. Here it's 95% for each of them. And here we have it in the upper tail. Here's 99%, same pictures, the z-scores differ. If it's a two-tailed test, the z-score is either -1, is both -1.96 and 1.96. I would go back and read that later. Here's what we just looked at. Below are often used confidence intervals. It's a z-score number line. The degrees of confidence. That's these percent numbers. Alpha is 1 minus the degree of confidence. In other words, if you're 95% confident, 1 minus 95 is 0.5 or 5%. The z-scores, the endpoints of the confidence interval, are given. They're called z-critical. All right, we went over these words, confidence interval. Alpha is 1 minus the degree of confidence. That's the red stuff out in the tails. Level of confidence is the probability a score is in your confidence interval. Here's your mean. You take your mean and you go up an error or down an error. If you're looking at a two-tailed test where the mean that your sample has could be either bigger or smaller than the population mean. Error is the maximum distance from the mean that still places a score within the confidence interval. Back to the fish tank. You didn't think I'd get back to it. That was your fish tank, for the record. Your mother, a math teacher, says your fish are getting too big. She says they were on average 70 millimeters long. That's 7 centimeters long. When you got them, you've been feeding them. They've been growing. They're getting too big for the tank. You, on the other hand, because you're not the mother, you're the child, you say, no, they're fine. They're still on average 70 millimeters long. Okay, we need more information, said the mother. One of my former students sold us fish. He was really into statistics and wrote some population parameters on this receipt, which I kept. Your fish tank population mean length was 70 millimeters. Your population mean length, mu, equals 70. You already knew the population had a standard deviation of 0.12. How did you know that? It was written on the receipt. And you got 70 fish. that means N, 80 fish. That means N is 80. That's big for a sample like this. Take 36 fish for a sample, measure them as accurately as you can. We'll assume the population is normal, and you can run a hypothesis test so we can make a judgment. Here's the formula for your test statistic, and you have no idea what she's talking about. Too many words? Let's just read them again. Remember, there were 80 fish. That means the population was 80. Standard deviation of 12. Mean is 70. The mean of 70 is mu. The test statistic, this is like the spread for the test statistic. Again, we go back to the data point minus the mean over the spread. Okay, this is what I next require my students to write down. That H0 is called the null hypothesis. Null means 0. The H1 is called the alternate hypothesis. The null hypothesis is what the world believes. The alternate hypothesis is what you, the researcher, believe. You may believe, even though the world believes the mean is some value. In each case, you might believe the mean is simply not that, or the population mean is greater than that, or the population mean is less than that. So here you have pictures of the kind of hypothesis test you're going to run. Old symbols, mu, the population mean, sigma, the population standard deviation, z, the standard normal score, alpha, the area under the density function, which is not in the confidence interval, and sometimes alpha is spread in 2 tails and other only in 1. The new symbols, K is for a constant, like the population mean is 70. Hypothesis, no symbol. A theory or statement which may or may not be true. H sub 0 or H0, that's called the null or original hypotenuse, or what everybody knows to be true. H1 is an alternate hypothesis, probably what you believe to be true. A hypothesis test is a procedure by which a hypothesis or statement which one believes to be true is tested statistically against another hypothesis already in use. Before clarification, swipe between the lines to see your answer. In the fish tank story, write the tank owner's hypothesis in symbols. Remember, the owner's the kid, that's you. What do you believe? You believe that the null hypothesis is 70. It's not what your mother thinks. In the fish tank story, write what the mother's hypothesis is. She believes that Doesn't look right. The mean is greater than 0. Let's just look at these two. No, I wrote it correctly. You believed, nah, they didn't grow anything. She believes, no, they grew, they're getting to be too big. Will the test be a one-tailed test or a two-tailed? One-tailed test or two tails? One-tailed test. The mother's alternate hypothesis is that the mean is greater than the 70. Use the common and confidence interval, which you have just seen, and state the number that is labeled Z critical at the 95% confidence level. Let's go back to the pictures. You want to use the picture and the numbers to state the Z critical at the 95 confidence level for a one-tailed test. So that no numbers there. No numbers there. Oh, this looks good. We wanted a one-tailed test. And we wanted it to be 95%. Looks like Z critical is 1.65. If we wanted to be 99%, our critical would be 2.33. I'm going to leave that there. Go back to here. Scroll down to where we are. So we want to find and state the number that is labeled Z critical at 95%. 1.65 matches our picture. Use the confidence interval. If you want to be 95%, 2.58. Where did the Z score, the Z critical numbers come from before they were put on the image? Where did they come from? The table of probabilities given the Z score. And I'm going to close this one, open this one. Here's a picture we looked at already. Here's the areas under the curve. Here's a Z score of 1.96. Here's a Z score of 2.58. I think that's what we wanted, wasn't it? 2.58. There we go. That's for a two-tailed. You want a one-tailed. That's 90%, 95%, 99%. So here's where we are so far. A hypothesis test is a procedure by which a hypothesis or statement, which one believes to be true, is tested statistically against another. In this case, the population mean, mu, was 70. The standard deviation was 12. N was about 80. The null hypothesis was the mean was 70, because that's what you believed. Your mother believed it was greater than 70. Alpha. How sure do you want to be? Well, we're going to use alpha is 0.01 or 1%. We want to be 99% confident. Up here, we want a one-tailed test. We want alpha to be 0.1. We want to be 99% confident. We get 2.33. Calculator will compute the test statistic for you. Here's what a picture looks like if you're handing it in to me on a test. Notice the normal curve is drawn. The mean is labeled. I wish to be 99% confident. That means alpha is 1% or 0.01. I have stated the null hypothesis and the alternate hypothesis. My Z critical, which I got out of the table, is 2.33. When I did the computation, and you could have the calculator or the web page do it, or the spreadsheet, you could do it in a lot of different places. Here I just did it with plain old ordinary arithmetic. You get the Z test statistic at 2.5. Well, what does that mean? Here was your critical. That's what the end of the confidence interval is. Your test statistics came out to 2.5. That's out here. It doesn't look like it's 70. Looks like it's bigger than 70. So you reject the null hypothesis, and I believe with 99% confidence that the mean is greater than 70. That's what it should look like when you hand it in. You could be wrong. I'm not going over the errors. It takes too much to explain the words. Here's the picture we just looked at. Again, here's a different one. Here's where all we believe is that the mean is not 70. In other words, it could be higher or lower. Ran the test. The test statistic is still 2.5, but the critical values, make it bigger, are 2.58 and negative 2.58. The test statistic is in the confidence interval. So you fail to reject the null hypothesis because the test statistic was within the confidence interval. I believe with 99% confidence that the mean is 70. So there we looked at a one-tailed test. Here we looked at a two-tailed test. Next, because we now have calculators that can do computation for us. When did they start using handheld calculators? They probably started using them in the middle 70s, 1970s. But they didn't get fancy until later than that. But once they got fancy and started to include more statistics on them, they were able to compute. The user was able to compute. It's called a p-value. And what the p-value is the following. Here's your confidence interval. Here's your alpha. There's your critical. But the calculator didn't bother computing the critical. It computed the area under the curve in excess of the test statistic. That's what this area is. And you put in your numbers. Normal, confident, cumulative distribution function. I think we have a mean here, test statistic of 2.5. I don't remember what the 10,000 is. 0 and 1 for your mean and standard deviation. There's what you get. So if this much is 0.0062, then this much is 0.9937. You're 99.38% confident. That's better than 99. Gives you more detail, and you'll find it on a calculator. I don't think I put it on the spreadsheet. I think you're good with that. I think you're good with this. You can now get the p-value using your calculator or the the cumulative standard normal. I'm not going over that. There are different types of hypothesis testing depending on what you want to test. Let's just look at, I don't want to go through all of testing. You'll see the same picture. Can I get there? Let's try this. Let's get rid of that one. And I think we can get rid of that one. We'll go back to here. Okay. Now, examine other hypothesis tests. We can go to either a web page or a PDF file. Or you could look at a whole video on the PDF file. We're going to go to the PDF file. This is a list of, I think there are like 20 tests here. This summarizes the tests and what they're tests for. Again, we're back to that fraction. Here's what used to be X and X bar and standard deviation. New minus the old over the standard deviation. If it's a Z test, that means it's a test. You're testing the mean, which is what we did. It's a normal distribution, which is what we looked at, and it's a large sample. Large samples are 36 or greater. That's why the mother told the kid, get 36 fish and measure them. The test statistics, because you were testing for the mean, it was your sample mean minus your population mean, the new minus the old over the spread. If the sample is less than 36, you use what's called a t-test, different table. If you're testing two means, there's your statistic. Two t's, two small samples. That's for independent, dependent. I'm not going into all that. Analysis of variance, 3 or more means using variance, and so on. Chi-squared, sign test, and then it also describes each test individually. I think you have enough.